All right, in this video, I will explain how to solve the problem 2.21 of your textbook, which also was in your lecture. So the system was a two pendulum that are connected via a spring, a linear spring with spring coefficient of K. Now there is a force F of t applied to this system from the environment, so that's your input. Now to write the differential equation for this system, usually like we start from a free body diagram. So usually when we are trying to do free body diagram, it's easier if we could draw the system with this deflection. So for example, here you see that on the right side, I have both of these masses deviated from the initial position. So you can see theta 1 and theta 2 here. Sorry, I'm going to correct this. So theta 1 and theta 2 here. So, and theta 1 and theta 2 are our angular displacement. All right. So for this system, we know that the mass, the length of the rod is L, and the spring is attached at the halfway point of each. So the spring force is applied at L/2 distance from the pivot point to these two in this system. Now, to write that, we need to draw the free body diagram. I always start from the part that the side of the system that the input force is applied, which means here. And the reason is that this will help us to understand how this first system will interact with the second system, because this force F of t is what makes the system move, right? So I'm going to draw the free body diagram of this first pendulum. So since this is a rotational motion, I know that I have to use sigma tau equal to I alpha equation for this. So the sum of the torques are equal to inertia, moment of inertia times the angular acceleration, right? So here for the first part of the system, first pendulum, I would be ml squares, because this is a pendulum connected to a rod, and then the alpha or the acceleration here is theta double dot. So here we will have theta 1 double dot for our first system. So this equation is just a general equation. Now, to do that, I'm going to draw this first pendulum. I have my pivot point, and I know that there's force F of t applied from the outside. The other forces are one from the gravity, mg, and the other one is force from the spring. Now, we know that gravity is always pointed downward, and to find the torque around this pivot point, the blue point, we have to divide this to its components. So mg sine theta 1 is this purple component, and mg cosine theta 1 is the red component. Now, how do I know that? So this, if the displacement here is theta 1, the angular displacement, you have this vertical line. If you draw another vertical line, then here would be your theta 1, right? So now this is the force in front of theta 1, so it's mg sine of theta 1. Now, if you look, only mg sine of theta 1 has this lever to create this torque. Mg cosine theta 1 is going through this pivot point, so the torque from this would be 0, because we don't have any deflection or lever. So same for our the force from our spring. Only the component of the force that is that has a lever to that pivot point will have an impact on the torques. So here we know F of k is k times x, right? So x here is a translational motion, but we have a rotational motion. So what we have to do here is to convert that translational motion to rotational. So if you look here, let me draw with, so here the deflection will be this deflection, right? So you have this L over 2 1/2 L times the sine of sine of theta 1. But we know that this spring is connected to both of these systems. So we also have to consider this displacement in here. So this is now, from here is just like our mass spring system. So we kind of took care of this translational motion and wrote it, and we can write it in terms of the rotational motion. So here we will have KL over 2 sine of theta 1 minus theta 2, which is only this component that has a distance of L over 2 to the pivot point. There will be another component here, which is through, and it will be K L over 2 cosine of theta 1 minus theta 2, but it's not going to impact, it's not going to have a torque, not going to create a torque on our pivot point, but the torque is 0. So we only have these 3 forces. So K over KL over 2 sine of theta 1 theta 2, mg sine of theta 1, and our ft. Now, if we use this equation here, then we have this term, which is our inertia term. So you can either use that equation, or as I explained before, you can use sigma tau equal to 0, but then the inertia, this ml tau theta double dot square, will appear as one of the torques. So to keep it consistent, I'm just going to follow this equation throughout this problem. Now, the direction of motion here is important when we're writing our equation. So let's say that if the force applies to the right and tries to push our mg up to the right, every other force wants to resist it, right? So mg sine of theta 1 is trying to creating a torque like this, while f of t is going to have a torque like in the opposite direction. Actually, it's the other way around. F of t is going to create a torque, in this direction, and then everything else wants to oppose that. All right. So writing the equations, we know f of t is applied at the halfway point of our rod, so ft times L over 2 minus all the other torques, because they want to oppose this motion. So mg sine of theta 1 times L, this distance here, the distance of the rod, minus this KL, this f of k, times L over 2, which is the halfway point. So here we calculated torque. So if we call it torque of mg and torque of k, that might be a lot easier to understand. And this is torque from force F, right? And this is our inertia. Now, if we rearrange, we can get to this equation, ml squared theta double dot 1, and so forth. And you see that here we have sine of theta 1 appear and sine of theta 1 minus theta 2. This is a nonlinear equation because we have theta 1, so we need our system to be LTI. So we learned last class that we can linearize it by assuming for a small thetas, theta 1 and theta 2, we can linearize this and write it as such. So we converted those sine of theta to theta 1, right? We got rid of the sine. Now, this is our first equation. For the second one, we need to go and write the free body diagram for this part. So the forces applied to this is from the K, same, but in the opposite direction. So I draw this pendulum. I have the same force, but in opposite direction. The only other force is my mass, so from the gravity. And if you write the component that actually has a torque is mg sine of theta 2. Now, writing the equation of motion, we have torque here. So I'm going to write a torque from K. This is torque from our mass, and this is our inertia, right? So writing that, and then if you continue simplifying and assuming for small theta 1 and theta 2, we can linearize this. This is linearize this, we get to the second equation. So we found our 2 equation of motions. So this is one of them. This is the first equation of motion. And this is our second equation of motion. So this is the first part of our question. The second part wants us to have the state space representation for the system. Now, we can use change of variable. You can also just think about theta 1 and theta 2 are your state vector, and then directly go from there. I'm going to use change of variable, just practice that. So we have two mass right here. So we have two theta double dots here. So this is the double dot one, the double dot two. So just from here, I can tell I need four change of variable. But if you remember in the last class, we said the minimum number of variable you need is the number of the masses plus the number of the restoring elements. So that connects them. So we would actually need three, but I'm going to solve this with four. Just will be a longer, a bigger A matrix, but at least that way you have a good practice on how to do change of variable. And if it was in the exam, it is acceptable if you use four like this. So I'm going to call x1 is theta 1, x2 is theta dot 1, and x3 is theta 2, x4 is theta dot 2. So my x, this is my state variable, is going to be x1, x2, x3, x4, which actually is theta 1, theta dot 1, theta 2, theta dot 2, which if you think about it is the angular position of the first pendulum, the angular velocity of the first pendulum, angular position of the second pendulum, and angular velocity of second pendulum. These are the things that I'm looking for. Now, we just simply put these values in those equations. So we are going to get, the x dot, the derivative of this x, because we know that we need to find x dot equal to ax plus bu. So x dot 1 is theta dot 1 from here, which is equal to x2. X dot 2 becomes x double dot 1. X dot 3 becomes theta dot 2. And x dot 4 becomes theta double dot 2. Now we can replace based on the change of variable that we have. So theta dot 1 is here x2, so I can write x2. For theta dot 3 is x dot 2, which I call it x4, so I can write these two. So these are pretty easy to write, so I'm going to start with them. Now I have two other equations, theta double dot 1 and theta double dot 2. They don't, I don't have them in my change of variable. You can see them directly here, right? But if you look at the equation of motion, you see that they are here. So 1 theta double dot 2 over there and theta double dot 1 over here. So I'm going to use my equation of motion to create these. So all you have to do is just rearrange and write them down. So theta double dot 1 from the first equation, and then theta double dot 2. Now you see that here I have still theta 1, theta 2s. So I'm going to convert all of those to my change of variables. Doing that, I get this four equations. So I have x dot 1, x dot 2, x dot 3, x dot 4, and I already changed all of those variables. So again, we are trying to create this ax plus bu. So I already have all of my x dot 1. I have x and u in here. So I'm going to create a matrix form, which is going to be this format down below. All you have to do is to populate, and you can always check. So this is 4 by 1. I have 4 by 4, and this is 4 by 1. So this is going to give me 4 by 1. So you're adding here, don't forget. And this is equal, is not S. All right, so I have my change of my state space representation, but this is just the state equation, right? This is a state equation. For this to be a state of space, I need an y equal to some cx plus some du. So here, since I have not been given anything, you can assume any output. So let's say I want my output to be to track, let's say theta 1 plus theta 2. I just want to know the difference. Or let's say theta 1 minus theta 2. Let's do that. I want to see how much is the difference between them, right? So I'm going to say theta 1 was x1, theta 2 was x3. So I'm actually looking for x1 minus x3. And then I can say that y is equal to, I have to create c times x1, x2, x3, x4, right? I'm going to move this over here, really easier to see, plus du, right? So here I have x1, I don't have any x2, I have -1 for x3 and 0. and then I don't have any u, so that's 0. So this is my output equation. So the two of them together, output equation and a state equation, are going to give me, so this is a state equation, are going to give me state space representation. Now, the third part of the problem asks for a block diagram. You should be all familiar with that. You can use these two equations directly to create your block diagram. And then you can check here that this system has one input. And since we are looking at two different displacement, you see that we have two output. Now, a lot of time when we are in, for example, Simulink, you can add a mux, which is a block that puts these two together. So basically you have a vector of θ1, θ2 that you're looking. This is still displacement, right? So that part is not needed, just for your information, but that's how the block diagram looks like. Hopefully this was helpful. If you have any question, please let me know.